Hello everyone, we will look at a problem on rigid body equilibrium. This time we will look at a cantilevered beam, or a beam whose one end is fixed and the other end is free, and then there are a series of forces or loads acting on this body. So here is the idea. Here is a rigid body, one end is fixed, so the entire rigid body here. And one of the ends is fixed. This is how we denote a fixed end, right? And then we have a series of forces and couple moments and so on acting on this rigid body. Now I'm going to draw a center line through this rigid body because a certain width is given to us for this beam. This is a really thick sturdy beam, and here are the forces acting on this rigid body. So at this corner point here I have a force of 200 pounds with a slope triangle 3, 4 and 5 given to us. This is the fixed end, or a cantilevered beam. And then I have a set of couple moment. There is one of them acting here, 200 pound feet in the clockwise sense. And then I have one more force which is acting on the top fiber of the beam, and that has a magnitude of 150 pounds. Some distance information is also given to us. Let's call the fixed end the point on the center here. Let's call that as the point A, all the way from the point A to where this force is acting, and then the end of the beam here. All those distances are also given to us. This is given as 1 foot, and this is half a feet here. And then distance from the center line onto the top and the bottom fibers of the beam are both given as 0.1 feet. Alright, so this is the entire rigid body. A pretty hefty rigid body, 1.5 foot long, and it has a width of around 0.2 feet, and then a series of forces and couple moments acting on this body. What do we need to do here? With a neat free body diagram, we need to find the reactions at the fixed end. Okay, so draw the free body diagram and find all support reactions. Alright, so before we set up the free body diagram and then find all the support reactions, let us first look at how a fixed beam or a cantilevered beam behaves in terms of its support reactions. So take a look at this from the next page. We will draw an isolated rigid body and show only the effects of the cantilevered support. So here is an isolated rigid body. We don't care about what's happening on the rest of the rigid body. And then this is fixed to the wall here by means of the fixed support here. And so we first set up a coordinate system. You can say, okay, positive x and positive y, and then some counterclockwise rotations treated as positive. So these are all planar problems, right? And so our rotations are either into the plane of the paper or out of the plane of the paper. Now you see that this is fixed. If it is fixed, it means that I will not be able to translate in the vertical direction, so translational motion is not allowed. I will also not be able to translate in the horizontal direction. You see, that is also not allowed. And you see, if something is fixed, if I try to bend it, there is going to be a certain resistance to the bending itself, which means that I am also unable to bend it. So if I try to rotate it, that is also not possible, which means that no translation at all. And no rotation. These are the fixed end constraints. And if this is indeed the case, then I can look at the effect of the fixed support by drawing the free body diagram of the rigid body, and instead of showing the fixed support, I can show its effect as a set of constraint forces in the x and y directions, and a reaction moment, which I can assume it to be either clockwise or counterclockwise. Okay, so if I draw the rigid body here, and if I want to show the effect of the support, I don't draw the fixed support itself, but instead I draw a horizontal reaction force. If I call this end as A, I can call this as AX. Then I draw a vertical reaction force, which I call as AY, and then I have a reaction moment. And this reaction moment, I can choose it to be either clockwise or counterclockwise, and I typically choose it to be counterclockwise, so that I start off in the positive sign convention to begin with. So this is the reaction moment. And these are the reaction forces. Alright, so once we have this, we are going to employ this on our rigid body, and then we can find out all these three. And you see that if I have a fixed support, then there is no other, there is no need for any other support, because the fixed support itself has three unknowns. And you know that in 2D rigid body equilibrium, you have only three equations of equilibrium. Sum of forces in the x and the y directions equal to 0, and then sum of moments about any arbitrary point is equal to 0. So I have maximized the number of unknowns to begin with, and so I do not need any other kind of a support if I have a fixed support on a rigid body. If I put any other kind of a support, then that's called as over constraining the rigid body, and this becomes an over constrained or a statically indeterminate problem, which means that we need to come up with some other set of equations to help us solve for the support reactions. We will look at such problems when we do mechanics of materials, where we look at fixed beams on walls, and then we will make use of certain kinematically useful equations in terms of displacements of one end with respect to the other. So for the time being, we will not worry about such things. Alright, so go back to our rigid body. We have a rigid body fixed at one of the ends. We have loads acting all over the rigid body. So here is the rigid body by itself. I have the center line of the rigid body, which I'm going to draw here, and then this is for me the point A on the center line. It's not necessary to label the center line point as a point A. I can call the entire end there as the point as the end A, but just for the sake of convenience, let me look at it that way. Then I set up the support reactions. I first of all have a reaction force in the y direction. I set up a positive xy coordinate system, which we can draw somewhere in the corner of the page here. So positive x and positive y, and then counterclockwise rotations are positive for us. So this is going to be AY, and then I'm going to set up an AX, and then I'm going to have a reaction moment, which I'm going to assume in the counterclockwise sense. Then I'm going to start drawing all the loads on the rigid body. I first of all have a couple moment. This couple moment is acting in the clockwise sense, and this is 200 pound-feet. Then I have a force of 150 pounds, which is acting on the top fiber of this beam. So that's 150 pounds. Then I had this force here, which was acting at a particular angle. If you go back to the figure here, you see that the force is acting at an angle. The slope triangle is given 3, 4 and 5. So this 200-pound force, I'm going to split it into a component along the vertical and along the horizontal, taking care to start the components from the point of application. So this is the point of application of the force, which means the components must come from those points. So the components must be in this direction and must be in that particular direction, right? And so if I make use of that here, so here is the point of application. A component along this direction is going to be 200 times 3 divided by 5, which is 120 pounds, and then the component along this direction is 200 times 4 by 5, or 160 pounds. Alright, so this is going to be the following. This is 120 pounds, and then this is going to be 160 pounds, and then I need to set up the dimensions for the problem. So here are the dimensions for the problem. From the end A here, where I have the fixed end, to where this force is acting, is a distance of 1 foot, and then this remainder distance is given to us as 0.5 feet, and then a distance from here to there is given to us as 0.1 feet, and this distance is also given to us. It is not needed, as you will see, but we will still write it out. Alright, so this is the entire rigid body, and we have all these applied forces, applied couple moments, and then we have the reaction forces which are acting at the fixed end of the body. And all we have to do is start using the equilibrium equation. So I start off with summing the forces in the positive x direction. So you see here, sum of forces along the x direction, all the forces pointing to the right taken as positive. This should be equal to 0. Do not forget that 0. A lot of times I've seen people forget the 0 there, and so you will not end up with an answer. So this is going to be AX. You see AX is pointing to the right. Any other force, I have this 160 pound force, so that's plus 160 is equal to 0, or AX is minus 160 pounds. And you see that when I started off the problem, I did not know the direction of AX, and neither do I know the direction of AY. I just took them to be in the positive x and y directions, and the same holds true for the reaction moment as well. I do not know what the sense of the moment is to begin with. That is dictated by how the loads are acting on the body, and then how the equilibrium equations pan out. Then I do the summation of the moments about the y-axis. I set them equal to 0, assuming that all the forces pointing up are treated as positive. What are the forces for me? I have AY, then I have the 150 pound force, and then I have the 120 pound force is equal to 0, and this gives me AY to be 270 pounds positive. In this case, AY turns out to be positive. And always be careful, the couple moment that you see here will not play a role in the summation of the forces. It will play a role only when you do the summation of the moments, and we're going to do that next. We're going to sum moments about the end A. We're going to set that equal to 0, and when you do the summation of the moments, you first of all see that this is a couple moment, the reaction moment A. That will not be equal to 0. That is existing at the end A, and that is what is giving you the resistance as you try to bend the beam. So I'm going to put that in there. So that's going to be MRA. Then I'm going to have this couple moment, 200 pound foot. You see that it's in the clockwise direction. Then I have the force of 150 pounds. You see the perpendicular distance is 1 foot, all the way from the point A on to where the line of action of the force is. And what is the sense of the moment? Right hand rule produces a moment that is into the page. 150 times 1 foot is going to be producing a moment that is in the clockwise sense. So this is going to be minus 150 times 1. Then I'm going to have some more. I'm going to come to these two forces at the end here. You see this 120 pound force. 120 pound force, perpendicular distance all the way to the point A is 1 plus 0.5, 1.5 foot. Right hand rule says that the moment produced by this is also clockwise. So this is going to be minus 120 times 1.5. And then lastly, the 160 pound force. You see, from the line of action of the force to the point that I'm interested in, you see the perpendicular distance is 0.1 foot here. Right hand rule says that fingers of my right hand aligned to the force. My palm is facing the point of interest, which is the point A. I curl my fingers. This force produces a counterclockwise rotation about the point A, and that's going to be plus 160 times 0.1. All of these put together is equal to 0. The only unknown here is the reaction moment here, and so I can solve for that, and I get MRA upon solving as 514 foot-pounds. Once again, key point here is when I do the summation of the moments about the point A, do not set MRA equal to 0. MRA is a reaction moment, which means that it will be existing and it will be counterbalancing the effort of all of these in trying to bend the rigid body. Thank you.